Excellent. Well, now that we're formally started, thank you for having me here. Thank you for hosting. I'm excited to join you all. Is there a way to remove that little? There we go. I'm excited to tell you all about the numerical construction of wave dark matter halos. Specifically, I'll be talking about fuzzy dark matter. This is work that has been in process for a while. I work at Columbia. My thesis advisor is Catherine Johnston, and I work with her on a lot of dynamics and galactic dynamics and stellar streams in particular. But alongside that, I also have been working on this project with Lam Hui and Sinew Leonardo, collaborator, both who were at Columbia. Sinew has since moved on to Perimeter Institute and CETA. But yeah, so I'd like to share this work, which has recently also come out on a paper. This paper we submitted a couple of weeks ago. It's about to be accepted, we think, because we just received a fairly favorable referee report. So it's very much in the final stages. But here we are to talk about these general ideas.
I guess the camera of the room is turned off. Sorry, I'm Matthias.
It's true. But can you see?
If it's okay, I only see the screen. It's fine.
Right. You're right. Let's do now. It should be yes.
Good. Sorry, good. And I don't think you can see me in the. There I am. Okay. No, but you can see me in my second picture. Good. So by means of a brief introduction to this topic, when we think about dark matter, we're pretty sure it's there. We see its gravitational effects, but the range of possible masses and theories out there is quite incredible. If you think about moving from a scale of 10 to the minus 20 something electron volts all the way to solar mass objects like primordial black holes, we're talking about almost 100 orders of magnitude, and it's pretty incredible that we are considering such a wide range of candidates for something that we are so sure is there, yet we don't really know what it is. Specifically in this large range, there's one boundary that I'd like to talk about, which is where we have to start thinking about the dark matter as a wave and not as a particle. So for any particle moving around, you can calculate its de Broglie wavelength from our undergraduate or even high school physics. And it's fairly straightforward to do it for these range of proposed masses, as well as for characteristic galactic speeds. And that gives you this nice transition point. And this transition actually relates not to necessarily galactic speeds, but just to the relation between the de Broglie wavelength and the interparticle separation. As soon as the de Broglie wavelength is larger than the interparticle separation, given a certain local density of matter, then you must start treating it, at least in that local regime, as a wave and not as a particle. And that in this kind of scheme of proposed dark matter candidates, and given our local presumed density of dark matter, happens around the tens of electron volts. So anything to the left of that dotted line, you need to start thinking about in terms of a quantum mechanical object and not a classical particle. Good. Now I will focus, this is not meant to be necessarily a particle physics talk, although I'm happy to field questions about the particle physics nature of some of these creatures, but specifically what I would like to talk about is the far left end of this regime, ultralight or fuzzy dark matter, where not only do you have to treat this type of dark matter as a wave on local scales, its mass scale is so small that the quantum effects have effects on astrophysical scale. So if you just calculate the de Broglie wavelength of a particle that tiny, that small, with characteristic galactic speeds, you arrive at a de Broglie wavelength on the order of hundreds of parsecs or even kiloparsecs, which means that you should start seeing quantum mechanical effects on astrophysical or even galactic scales. Now, just as a means of a disclaimer, I'll focus on ultralight dark matter and galactic applications, but the method I'm going to talk about for simulating wave dark matter is actually applicable for this entire regime on the left, and may also be important if you're interested in, for example, direct detection experiments of something like a QCD axion, in terms of understanding how to what its structure is locally and how what is the likelihood, say, of detecting a particle like that on in an Earth-based detector. So applications for this, I think, span the entire range of wave dark matter proposed candidates, but I will focus specifically on the galactic applications. So there are a few very convenient consequences of having an ultralight particle at the 10 to the minus 22 electron volt regime. The main one is that on large scales, on scales larger than a galaxy, it reproduces exactly what we expect from cold dark matter, because again, on scales larger than, that are much larger than the de Broglie wavelength, say on a scale of a megaparsec, as you see in these simulations, the overall global structure is expected to be more or less the same. So if you kind of squint and look and compare the fuzzy dark matter simulation on the left here to the cold dark matter simulation on the right here, and you look at kind of the overall global distribution of structure, it looks more or less the same. And that's very good, because cold dark matter does very well on predicting large scale structure of the universe. So this is very encouraging. Furthermore, when you look at the smaller scales, at the scales of the where the quantum mechanics start mattering, you see these nice looking interference fringe patterns. This is from one of the simulations that really started out the interest, or that reinvigorated the interest in fuzzy dark matter, looking at kind of the cosmological formation of dwarf galaxy-sized halos. These interference fringes have effects in terms of kind of the small scale structure effects within a galaxy. And in particular, this scale size of approximately a kiloparsec, where you start seeing quantum mechanical effects, is very convenient, because what ends up happening is a particle like this will smooth out structure on those smaller scales. You truncate the mass function, you get rid of smaller satellites, you get rid of cusps in the center of galaxies, and those are all very convenient, because those have been debated for a while as tensions between cold dark matter only simulations and what we actually look to see around us in observations. We don't really see cusps, density cusps in the center of dwarf galaxies. There has been a long debated missing satellites problem, or a too big to fail problem, in terms of how many bright satellites we see around us in the Milky Way. And all these can be explained away very conveniently if your particle is at the scale such that you have quantum mechanical effects that smooth out small scale structure. Now, this isn't to say that I'm going to champion only fuzzy dark matter. There are various ways to deal with these problems with just cold dark matter. They usually involve playing with feedback and a variety of other levers that you can tweak. So this isn't to say, and I should also say there are plenty of other tensions that fuzzy dark matter creates. This is just why it is a generally interesting field, and why it would be nice to have a convenient way of simulating it. Which brings me to the main inconvenience of, talked about this, the main inconvenience of having an ultralight particle is that it is extremely hard to simulate. Unlike cold dark matter, where you can leverage things like adaptive mesh refinement techniques and zoom into various areas of your simulation while looking at a large cosmological box, to correctly capture the behavior of a quantum mechanical beast like fuzzy dark matter, you will always need to resolve down to the de Broglie wavelength in every cell, so to speak, of your box. Question?
So yes, I'm familiar with the changes in density that this type of dark matter model would produce, like the ones that you just mentioned. I'm wondering if it might also, in certain cases, lead to like having a kind of screening for potential, like, where there might be variations, tiny variations in the fine structure constant, for example.
Certainly, fine structure constant. Well, I can speak more broadly that for any large scale effects, you can basically reproduce everything you see with typical particle-like dark matter.
Yeah.
It's only when you get to those smaller scale substructure kinds of effects that we start seeing differences.
Yeah.
I have to admit, I haven't thought carefully about the consequences on fine structure constant. I will say that those are the tests that are of interest. That's how you differentiate between this and. Good. So the current state of the art of large simulations, kind of full-fledged simulations that solve the Schrödinger-Poisson system, which is what you need to solve in order to simulate fuzzy dark matter. The current state of the art is we can simulate a few dwarf galaxies in a relatively large-ish box, but we haven't even reached the point where we can simulate the formation of a single Milky-Way-like halo for fuzzy dark matter. And the main issue is, again, it's numerical complexity. Getting a box that's large enough that still resolves down to the de Broglie wavelength at every point in the box is currently computationally an intractable problem.
One question, in this figure that you have, like all of this structure, like, you know, what is different from, say, CDM, is that on the scale of the de Broglie wavelength? Are we seeing the de Broglie wavelength? That's what sets those things?
Precisely. So, yeah. Sorry, continue.
Yeah, and the second question would be, on one time scale, are those structures changing?
Good. So certainly the kind of the density fluctuations are very much on the scale and set by the de Broglie wavelength, the de Broglie volume. There are obviously changes as you move further and further out because the velocity is also changing. It's not just the mass of the particle that matters. It's also the local velocity that sets the de Broglie wavelength. And the time scale similarly. So in the center of halos, we're talking about characteristic timescales on the order of tens of mega years, whereas when we get further out to kind of the edges of halos, we're talking closer to hundreds of mega years in terms of kind of the typical frequency of a single wave. And of course, the main thing here is the frequency differences, the interaction between the various waves, but those are also on a similar scale.
But this is much shorter, I guess, in time than some sort of typical dynamical time that you would use in a CDM simulation, the orbits of the particles in the location or something.
Yeah, so I mean, when you look at the dynamical, there's probably a fairly reasonable order of magnitude estimate, but certainly kind of the dynamical time of the halo, you know, a particle moving all the way around at the edge of the halo is much longer than the typical fluctuations in that local vicinity.
Mm-hmm. And you think that you think resolving then those fluctuations that are like transient and changing all the time makes a difference?
Yes, it certainly does, because part of the reason these structures hold is from the quantum pressure from these fluctuations. This is kind of the main reason that you see the stability of these structures. Similar to, I mean, I guess the classical equivalent would be that you've got a bunch of subhalos zooming around and giving you some form of kind of global pressure that keeps the structure like this alive. In the same way, it's these quantum fluctuations that provide the pressure to keep a structure like this stable. So if you don't account for that, you end up seeing simulations that either fall apart or don't at all reproduce anything reasonable looking like a galaxy.
Yeah, no, I was just thinking that you could model them in some effective way or change the mass to make it don't need such a good resolution. If you don't really, I mean, if you wouldn't have such a big effect on larger scales. It's just you can compute the time correlations or some other scheme. I don't know.
It has been done, and there are certainly effective ways of trying to kind of make those shortcuts. Certainly, you can make some generalized assumptions about the overall scale and structure that you would get. In particular, for kind of my field of interest, which is the intersection of this and galactic dynamics, you can make various assumptions on, you know, how long one of these interference fringes lives, what is its characteristic timescale, and how fast does it move, and can you then approximate this quantum structure with some sort of a classical particle or blob that lives for a certain amount of time. That's all doable, and that has been done, and there are preliminary results from that. It would certainly be nice, though, to compare those to actual behavior in a large simulation. And I would say that kind of our work and what I will talk about is very much kind of the middle ground between something that is both very true to kind of first principles, full-fledged dynamical simulation, but so it's not that it's much faster, but it also is more accurate and more, it captures much more of the physics than making some of these first order assumptions, approximations to try to treat these kinds of things classically.
So the timescale for these interference fringes is?
It ranges for and again, this is don't necessarily quote me on this, but we're talking about anywhere between about 10 megayears for central blobs where there's things moving faster to tens to hundreds, low hundreds of megayears out in the outer halo, which is approximately the dynamical time of
to get that, I just take the de Broglie wavelength multiplied by the orbital speed of that.
at that rate, yeah. So I mean, and you know, if you assume a flat rotation curve, then it's not actually changing all that much. The local density is changing a little bit, so that you're changing by about an order of magnitude as you move out.
Is it possible you might, you know, with pulsar timing, see some of the signatures?
If you had a great way of quantifying exactly how those signatures are different from cold dark matter signatures, then certainly, and I think that's where this work gets at, is, you know, can we put together a variety of tests that very clearly mark out, say, the difference in the acceleration field between a particle picture where you have, you know, subhalos zooming around versus interference fringes that evolve on somewhat different timescales that have different that have a characteristic size, which is governed by the de Broglie wavelength. So certainly that is a test of the many tests that we envision looking at. Let me briefly continue. I just want to talk a bit about the method that we've put out, and then I would actually like to spend most of the time, or at least discussion, on applications that we have envisioned and seeing if there are any other suggestions from the room. The general problem, and this is the problem for anybody simulating fuzzy dark matter, is to solve the Schrödinger-Poisson system. Essentially, the equation of motion that governs the quantum mechanical behavior plus gravity. And in our case in particular, we're looking for a nice, either analytical or numerically solvable form of the wave function psi that goes into both of these equations self-consistently. Basically, do you have a psi that evolves based on the Schrödinger equation and that sources its own potential, such that that influences back into the potential? And here, if you have something that solves both of these equations simultaneously, presumably you found an equilibrium steady state for a fuzzy dark matter halo. We make a few key assumptions to make our life a little bit easier, and I'll talk about how we can actually relax some of these assumptions. First, we assume general time independence. We assume that our halo has reached some form of equilibrium. It's not interacting with other things falling in. It has more or less kind of reached its approximate shape. This allows us to project the time-dependent Schrödinger equation into the time-independent form. And then we can construct a wave function as a superposition of a bunch of spatial wave functions that each have their own characteristic timescale. We talked about the timescale already, so you're all already thinking along those lines.
Sorry, may I ask a question? You say time independence, and now there is e to the minus.
Good. So we're just assuming that the spatial form is not changing, and that so basically psi is not changing. So then the exponential term solves this equation.
Okay. Sorry.
But we're assuming that the dependence on x and the dependence on t are separate.
Okay. Sorry.
No, it's a good question. Furthermore, we can then look at the density field, which is this waveform squared, and we can decompose that into the cross terms and the off diagonal terms. And since all of these eigenmodes are orthogonal to each other, and if we assume random phases for each of these modes, we're assuming that there is no kind of correlation between the individual phases of each eigenmode, then in a time-dependent sense, you can get rid of the cross terms, and you only need to deal with these diagonal terms. So basically, your expression for the time averaged density field becomes very simple. It's just independently each of the individual eigenmodes squared along with their amplitudes.
But aren't the cross terms exactly what give you the blobs that we were looking in the picture?
Certainly. Now, we're not going to forget those cross terms. What we're looking for is a stable global configuration such that after we've constructed something that is stable, you can then re-look at this equation, solve for the full equation to find your interference, which is exactly as you said, that is what gives you the interference pattern. However, the general assumption here is that the global shape of the potential is unchanging. And so you don't have to think about these cross terms in order to solve for the steady state solution of this equation here.
Thank you.
Finally, we'll assume spherical symmetry. We mainly assume that because solving the Schrödinger equation for a non-spherical cases is not fun. It's not. That isn't to say that we can't do that. It's certainly one possible extension, maybe to give as a project for a grad student in the future. But at least as a proof of concept, we're looking at spherical halos, and that's, I think, also it would be very beneficial for the field, even if we only came up with an efficient way to simulate spherical halos, since that is more or less what we expect, with, of course, departures to triaxiality. But generally, that seems like a good assumption for what dark matter halos look like. So spherical symmetry means we can decompose the eigenmodes into a radial and an azimuthal component and solve them in the same way that you solve them in undergraduate physics. And here is kind of just a picture of the first few radial eigenmodes that solve an equation given a certain galactic potential. So you can see kind of the characteristic scale here, and you find these fringes happening at around the de Broglie wavelength type scale. This up here in the top left is your ground state, no angular momentum, so it does reach the very center, and no higher n modes that give you these.
Yes, that's a stupid question. You said spherical symmetry, but then there is also M and L different from 0.
Good. We're assuming spherical symmetry in the sense that, oh, that's too far. We're assuming spherical symmetry in the sense that the global solution is spherically symmetric, which means that these R modes, the radial dependence is separable, and these are simply just the spherical harmonics. And so if you populate all the modes evenly, you'll still get a spherically symmetric beast. This is somewhat similar to solving the hydrogen atom.
Yeah.
Which you make the same kind of spherical symmetry assumption. The global potential is spherically symmetric. The individual eigenmodes are not spherically symmetric, correct? But their superposition will be. And again, Matthias's comment is again correct. They're spherically symmetric in the time average sense, but if you put back the time dependence and look at the interference, then of course you're going to get non-spherically symmetric structures.
Sorry, another difference with the simple quantum mechanics problem is that there you know V in the hydrogen atom. Here you haven't told us what V you are using and how.
Terrific. Good. So you asked the leading question, which is we don't know V, and I also haven't said what the amplitude of each of these individual eigenmodes is. The challenge is to find some sort of a configuration, some sort of a superposition of these waves that sources a V that then solves that then basically you need your psi to both induce that potential, but you also need that potential to source your psi. So you need something that kind of is circular, gives you something self-consistent. And the challenge here is to deduce what is a stable configuration that gives you a potential, and does that potential look like anything that we see in terms of like observations? Can we match galaxy or halo profiles that we think exist? Can we match, for example, an NFW profile of a galaxy? There have been a few attempts to prior work that we base this off of that make various assumptions to give you that answer. What is V? So work from 2018, looking at simulations, decomposing them, finding what is the distribution function in terms of that kind of leads to that those amplitudes of waves. That then source something that is in theory stable because it's stable in the simulation. So you can extract from a simulation. So on the left here, this is the work from, this is the simulation from which they extract a set of amplitudes. And then they can recast those amplitudes to build something that looks more or less like that simulation. So this is on the right. The only difference here is that this took a long time to simulate over a big, large supercluster of computers, whereas on the right, all they did was they plugged in amplitudes into the numerically calculated eigenmodes that we solved on the last page to produce a picture that looks very similar. The only drawback here is that this is based on an existing simulation of being able to draw the distribution function from there. More recently, Neil Dalal and friends in Toronto have looked at how you can draw amplitudes directly from the distribution function by inverting a potential. So if you say have a potential you're trying to match, let's say you're trying to match an NFW potential, it's spherical, you can invert that using the Eddington formula to extract a distribution function. You assume isotropy in that case, and you can then figure out what the amplitudes of each eigenmode based on their energy should be to give you a steady state solution. Again, it's a solution that sources that potential and solves it self-consistently. And you can see again the same looking structure that we saw in all the previous plots, but again, this is solved numerically and analytically, not using a full-fledged simulation. And in Neil's case, they used this to investigate the effects on stellar streams in galactic potentials. Very nice, again, very efficient use of being able to solve for these quantum mechanical halos without having to simulate them from scratch. Our method basically builds on those, extends them a little bit. We use the approach that was originally developed by Martin Schwarzschild to construct classical triaxial halos. The general idea for the original Schwarzschild approach is you start with a target density profile and potential that you're looking to match with a series of classical orbits, stars basically. In that potential, you can integrate the orbits that exist within that potential sources. If you can then calculate the contribution of each one of those orbits to the density field. So basically, if you have a star in each orbit, that star spends a certain amount of time at each cell. We just heard Scott talk about something similar where you assume that the orbits are basically a rigid wire, but here we're talking about galactic orbits that precess and that move around. But you can essentially calculate the density contribution from each individual orbit. And then the challenge becomes, can you superpose a large library of orbits that exist in the original potential to recreate that potential? And if you can, then you have essentially created a self-consistent galaxy made out of classical orbits, and those orbits source the original potential. So that should, in theory, live for a long time because it's self-consistent and stable. We take the same idea, except instead of orbits, we have our quantum mechanical eigenmodes, and each of those eigenmodes individually give you a density form. Again, we're assuming time independence here, so you take just the squared form of each individual eigenmode. And the question is, can you superpose those eigenmodes to recreate a target potential? In this case, we've chosen a potential that's very conducive to fuzzy dark matter, which is an NFW outer region with a superposed solitonic core. These are the potentials that are seen in many dynamical simulations of fuzzy dark matter. But this is just our test case. We can actually do this for any potential that we want. We can choose any potential, see what quantum mechanical eigenmodes exist in that potential, and then recreate the potential with some clever superposition of those eigenmodes. And so if we can resource that, in our case, what we need to do is we actually need to iterate a few times. There are a few constraints that don't exist in the classical case for us. In particular, we can't, with fuzzy dark matter, solve for a density cusp. There are no eigenmodes that give you a cuspy inner profile. So if you start with a target potential that has a cusp, you will be forced to, at some point, truncate that cusp based on the allowed eigenmodes that you have, which means that you're always going to have some departure from your original target. So the reason we do a few iterations is to make sure that we've reached a point where the input and the output potential have basically converged. They're not continually changing.
You say there's no eigenmodes that have a cuspy profile. That must be built into the Schrödinger-Poisson system somewhere.
Correct.
Where is it?
That comes from well, the initial conditions that you assume for solving well-behaved Schrödinger solutions are such that you at most can level off in terms of your density as you approach small r.
But that's being put in as an assumption.
That's being put in as an assumption, but that is, I mean, I guess you can't have, well, I mean, from first principles, you can't have structure smaller than the de Broglie wavelength in quantum mechanics. It doesn't know to be there. So I mean, these are, I guess, the assumptions of a generally solving the Schrödinger equation. I mean, you assume continuity at the origin, basically. You can't have a wave that peaks in the middle. So and you are limited by your de Broglie wavelength. So if you want to model a cusp, you can make your particle size larger and larger. Your ground state's going to get smaller and smaller. You'll get closer and closer to modeling cusp. Of course, you can think about cold dark matter as a quantum mechanical being as well, and solve these equations and get the same answer down to a certain scale, which is insignificantly small. But there's no point to do that because classical physics captures that equally well.
So I'm just wondering, you know, and I don't have a solution to the problem of finding the amplitudes and the V's either, but I'm just wondering if how much of a you know, how much of a caveat the way you're sourcing this potential from traditional static potentials causes in this construct, which, you know, I mean,
it's a good question. It definitely introduces some caveats. So, for example, the caveat of time independence that we've reached in an equilibrium state is a strong caveat, right? Because we know that there is no galaxy that lives in complete isolation. There are things happening to it. There is the caveat of, I said, spherical symmetry. We know that galaxies have all sorts of non-spherical structures. Having said that, part of the goal of this approach is to make a more qualitative statement, which is, you know, we see galaxies that have, you know, something like the Milky Way, which hasn't been significantly interfered with. Maybe you'd say the LMC is a significant interference, but that hasn't had a major merger for a while, that takes on a fairly equilibrium-like shape. And we know more or less what the density profile should look like. Part of the question here is, if we were to assume that fuzzy dark matter is what makes up this galaxy, what would it look like? Can we model that to match the density and the potential that we believe our galaxy, our dark matter halo has? And what consequences does that have? So this isn't to say that you can use this to necessarily rule out a certain shape or arrive at the most natural V for fuzzy dark matter. Rather, the goal here is to say, given a V, what would fuzzy dark matter do in that V, and can we model it more efficiently than just throwing it at a full Schrödinger-Poisson system to give us the solutions?
So sorry, when you compare, to the classical approach based on the Eddington formulae, where you do the same exercise except you work in velocity space or energy space, I guess your quantum states must be distributed in a discrete sense as a function of energy in a very similar way than a classical, using the velocity dispersion kind of approach. You see what I mean?
Yes, that's a great question. I've got the slide here just to address that exactly. So here's a solution. And again, the way we solve this is we just let the computer optimize for the best fit set of amplitudes that match our input density profile. And if you look at, so here in this, so on the left, you can see how we've exactly matched our density profile with a little blip here, just because we have a Heaviside function to govern the transition from the outer profile to the soliton core. On the right here, you see in the dashed line is the classical Eddington distribution function, and the blue crosses are the amplitudes of the individual eigenmodes found by the algorithm that's meant to match the density profile. And you can see that once you get to the high energy regime, where you have basically a continuum of energy states, it more or less condenses to that classical form of the distribution function. But out in the sparse region, where there are very few density states, that's where you get the departures. Does that answer the question? I think that's exactly what
Yeah, it's exactly. I asked too early. Sorry.
No, you led exactly to what I wanted to talk about. Very good. And so that actually allows us to make an even easier method, which was we can assume isotropy and thus constrain kind of bins in energy space and arrive at a very similar solution. And that means we're solving for, instead of something like tens of thousands or hundreds of thousands of eigenmodes, where here we're just solving for, say, 50 bins in energy space to provide an isotropic halo. And again, that still allows for that variation and for you to move the amplitudes around when you reach the sparse region in energy space. And we've actually, in an appendix to the paper, if you're really interested in this, we actually show, we kind of reproduce some of the original WKB calculations to show exactly how this condenses to the, or converges to the classical regime, and that the assumptions kind of do it, that if you, especially if you're looking to model kind of out here in the halo, you can certainly just assume the distribution function to model this very efficiently, rather than using the full formalism that we've laid out here. Now back to Matthias's question earlier, we obviously are very interested in the interference fringes that you get from this, and all we have to do is, now we have the amplitudes, we know the energies, all we have to do is plug this back into the original psi function, and we get something that looks exactly like the halos that I showed before that came from the dynamical simulations, but here we've produced them on my laptop in about 3 minutes, as opposed to doing it over a day on like a 100 core system and so on and so forth. And you get kind of very similar behavior with fluctuations in density and these evolutions of these interference fringes. We show that, oops, there we go. We show that you can actually, if you take a snapshot of our constructed halo and plug that as initial conditions into a full-fledged simulator, and we can basically evolve one analytically just by propagating the phase, and the other one evolves in the simulation. Whoops. Okay. The other one evolves in the simulation. You can see that overall the structure looks very, very similar. Individual kind of interference fringes will not exactly be reproduced, because then you actually care about the gravity on a micro scale that's affecting these things. But globally, the structure is very, very, very similar. And kind of in terms of the statistics, if you're looking for like a 2-point correlation function within this halo, all these things that we show are very well preserved in our constructed halo simulations compared to the dynamical simulations. If you really want to look for differences between these two rows, then I point to the corners of the simulation box, where we actually have effects because it's in a corner, and this is a periodic box, so things are flying in between. So you see kind of weird looking structures appear here where you don't see them up in the top row. And that's because in our top row, we're just solving this radial set of eigenmodes and propagating phases. So you don't see corner effects in that simulation. But the main takeaway here is these things look qualitatively very similar. Qualitatively, they look very similar. I don't know why it keeps moving around like this. The overall behavior, so the orange lines here are the dynamical simulations, the blue lines are the are constructed simulations. They maintain the same density profile over cosmological timeframes. So here we've evolved a 10 to the 10 solar mass halo, compared its density profile in a dynamical simulation to our constructed simulation, and we show that they both maintain a very similar structure over basically the age of the universe, which is what we care about. Furthermore, in our paper, we show that you can recreate a variety of different density profiles. It doesn't have to be this NFW plus core. So here we've played with density profiles that range from an isothermal sphere, density decreasing is r to the -2, out to a plumber fit, which is a much steeper decline in density out in the outer halo. In all these cases, the fuzzy dark matter fit does very well to produce a stable configuration. The main difference, of course, is you can't create density cusps given your de Broglie wavelength. So for the particle mass we've chosen, you always end up with a core at a certain scale. But in terms of modeling kind of the outer behavior of the halo, you can basically choose whatever halo you want to model and use this machinery to model it, and then investigate what happens. out in these regions of the halo in terms of the interference fringes effect on, say, baryons that are moving around.
So in normal n-body simulation, the output of the simulation is 6 numbers times the number of time steps. Right? Some huge list of data like that. What's the output of your?
I can match that because basically so the output of a full dynamical simulation would be that as well. For fuzzy dark matter, you're just, I mean, your output would normally be 6 numbers, which are the real and the imaginary part in each cell, because you have a psi which has, but that gives you 60 information.
Right.
And you have to solve that in a grid. And of course, for a large enough simulation, that grid is so fine that that's why it's computationally intractable.
Tell me the density and potential
But
as a function.
all I need to do to give you that equivalent list is to, where are we? Density profile. Sorry, I just want to find my psi. All I need to do is calculate. So I have a library of eigenmodes that are, you know, say some 10,000 or 100,000 functions, which is something relatively easy to store on a laptop. And as long and you just plug in the grid that you're interested in, you plug in the times, and you output the exact same list. You can even do better, which is if you're interested in a localized region for that halo, you don't have to output that full, you know, grid. You can just, if you're looking at like a stream at a certain radius,
Right.
then you output just in that
So
radial bin.
a stream as a bunch of test particles into this background.
So now you have basically all the tools you need. You have the potential and the density. You can calculate the acceleration to calculate the behavior of the stream in this background. And again, you don't even have to simulate the whole background. You can figure things out locally. I mean, for the acceleration, you do need to take into account the global thing, but you can again do that very efficiently here compared to trying to simulate this in a full-fledged simulation.
But presumably for looking at the perturbations themselves, it's not a global thing, right? Because it's maybe
Correct.
it's maybe, I don't know, some multiple moments of the thing, because it's already in this part. Yeah.
Exactly.
It's
I mean,
rather local, right? It's still
it is
rather
very local. If you know, if you were trying to simulate this in the traditional sense, you wouldn't be able to find those local structures without, you know, building something up self-consistently globally. But here we have, I guess, the point of this is to say we can create something that mimics the behavior globally of these halos, and you can easily extract the local behavior very efficiently compared to actually simulating the whole thing and, you know, using the traditional dynamical Schrödinger-Poisson solver on a grid.
Now I can put a binary into this and see what happens to the binary.
So you can put a binary into this and see how quickly the interference fringes disrupt the binary. You can put a stream in and see if this looks anything like some halos punching through, if you can create GD1 with a gap in it because you have one of these interference fringes that happen to fall in the right place. You can even try to put a disk in it to see if you get disk flaring. Although at a certain point, you get to the point where you also want to think about the interaction of the disk back on the halo, and then that we can't do because we've assumed a steady state potential. But certainly another great application of this is there's a lot of work looking at what happens in the bulge or even in the nucleus near the soliton. You know, does this kick out, does this heat things on that? Does it kick out stars that are orbiting kind of near the center because you're basically injecting energy through this wave interference? So you can easily model that using this this method. Let me just skip to my application slide because that's what we're talking about.
I'm using this word soliton. Can you point at me something on those pictures and tell me why is this soliton?
Good. So the soliton is the essentially the ground state. So in the traditional picture here, over time, you get a Bose-Einstein condensate in the middle. Basically, states, particles or waves will converge onto the ground, will cool down into the ground state, giving you an overpopulated ground state, which is what we refer to as the soliton. So this is work by Sinew Lee, who's a collaborator in our paper and used a lot of the methods that I just described to look at the behavior of that Bose-Einstein condensate and look at it in full-fledged simulations and decompose it and see what is going on. In kind of the seminal works on fuzzy dark matter from 2014, kind of the first time we really had computational power to see cosmological formation of this. What those works tended to show is that the global structure of these halos is NFW-like on the outer region, and the central region has this core-like feature, an overpopulated core. Actually, so you see this in all of these because we use that as the target density profile. But you get this overpopulated core, which is basically the overpopulated ground state, kind of punching above the rest of the density profile, and then of course leveling off because the solution has to level off as R goes to 0. So that is, when I say soliton, that's I refer to that ground state. That soliton is not perfectly stable because you still have excited states that are interfering with the soliton. So as a result of that, the soliton will move around. It doesn't always stay exactly in the center of the halo, or it looks like it's traveling around because you've got these excited states that are interfering with it, that are causing both constructive and destructive interference, causing it to look like it's doing this little random walk around the center of the halo, so the center of mass of the halo.
So in some plot before, you had like the amplitudes of these different modes, I guess, compared to which one is the soliton ground state? It should be way up somehow in this.
Yep. So here we show, so in this configuration, you can see the soliton here is about a factor of 2 above the next. There's one other excited state here that gets heavily populated.
What is the y-axis now?
The y-axis here actually, so it's the mass that exists in each eigenmode. So it's basically the shape of the eigenmode times the particle, or so the number density of the eigenmode times the particle mass. And so you actually get kind of
integrated over the entire, so like the size square over the.
Yeah, exactly. Integrated over the size of the halo. So, yeah. But of course, for the soliton, the thing truncates much before the halo. This basically tells you how much mass is in the ground state.
And I think of the ground state as one of these spherical harmonic things, or is it a superposition of a few of them?
The ground state is the 0-0 term of the 0-0 eigenmode.
That's right.
Exactly. No angular momentum, no additional fringes. I'm drawing this.
It's not so much higher, the soliton. I guess there's many things within an order of magnitude.
True. And I think that's part of. So if it were very, very much higher than the rest of the states, then you would not expect any sort of random walk of that kind of central density element. Because there would be nothing that would be strong enough to interfere with the soliton state that was too elevated. But because the other states kind of are strong enough to at least compete with it, you do get effects that cause the central density to fluctuate a little bit back and forth. That is both what we see here, but that's also what is seen in the full-fledged dynamical simulation. So it's, I mean, in a sense, we're just reproducing that here. I think it's also important and interesting because that's one of the testable consequences of these models, is that you should see some sort of, I don't want to call it an instability, but you should see some dynamical behavior that it isn't just a stable kind of density core at the middle of fuzzy dark matter halos. You should actually see the effects of interference fringes all the way down to R = 0.
But is this something that you somehow put by hand when you put the profile that you're fitting, that the 0 mode is not so high? Is this something to the, your profile that you put there, your target density profile?
It certainly has to do with the target we've chosen. I mean, the reason this mode here is elevated is probably because it needs to match kind of the density right after the transition away from the soliton. So, if we were to, instead of an NFW-like halo, which transitions to R to the -1 below the scalar radius, if we were to take that to R to the -1/2, for example, then certainly you could elevate the soliton more and get less of this kind of competition with the ground state. That's definitely possible. Here, what we've done is we've just tried to match, I mean, in this case specifically, we just use the target profile to match target profiles out of simulations of fuzzy dark matter. But you could certainly play with your target profile if you were looking to create a fuzzy dark matter halo with no interference to the soliton. You could definitely play with the outer halo so that you just have kind of a soliton and all the other states are an order of magnitude lower, for example.
But this property might depend also on the halo mass. Or is it?
The property may depend also on the halo mass, right? There is a lot. So one of the ways we've looked to apply this, I think a lot of recent work on fuzzy dark matter has related to, is there a relation between the halo mass and the core mass or the soliton? Papers claim there should be, and I think if you just start from first principles and thermodynamics, you should expect some sort of a relation between the shape and population of the ground state to the global mass of the halo. Those usually take the form of some power law, like in the soliton mass scales of the halo mass to the minus to the 1/3 is the typical one that's quoted in much of the literature. And that comes from, again, from looking at simulations and trying to play with the mass scale of the halo and seeing if a certain trend emerges for the soliton size. What we can do here is we can plug in those target profiles and then play with that relation. See if we can create a target profile that has a different soliton mass and see, does it remain stable, or does fuzzy dark matter prefer to return to some power law relation between the halo mass and the core mass. We have some preliminary work in the paper. I don't think I have it here. Let's see if I have it in some of the backup slides. Oh, here it is. Yeah, so we actually play with using different kind of ground state populations, different shapes for the ground state to see if the amplitude of this ground state stays stable when we plug in what we think is a stable construction into a full-fledged dynamical simulation. Does it retain the original shape? You can see that the small scale time fluctuations are pretty big, but globally, in all three of the cases, the amplitude of the ground state stays more or less actually where it was originally. It doesn't seem to all converge onto one of these three constructions. I should caveat this by saying this is extremely preliminary. We mostly did this just to showcase how one might use this method to investigate something like a core halo mass relation. I would say preliminary, this indicates that you can have a variety of stable configurations. But again, the main goal here is to show this is how you could actually approach this. If I were actually, and we actually plan to do this, I would actually populate something like a grid of 100 of these and see how each of them evolve and see if there's a more statistical trend towards some sort of a power law relation. But this is at least a preliminary demonstration of how we can start addressing questions like this with our construction method. So we already talked about our plans for what comes next. We have a lot of ideas for what to do. Some of these we've already discussed. So we can certainly investigate the properties of fuzzy dark matter halos. We can look at the statistics. We've already started doing that simu-Lie, and CETA is actually looking at the 2-point correlation functions and higher order statistics to see if there are any clear differences between this and cold dark matter. In particular, we're looking for a signature at the de Broglie scale, which is what we expect. We can look at, we can use these simulations for efficient models of stellar heating, to look at nuclear objects, to look at the bulge, to look at the disk, to look at scattering of tidal streams, things that have already been mentioned in the room here. I think one of the more promising outcomes of this is we can actually extend our construction to larger halos, because again, for us, it's very easy to do that using this method as opposed to full-fledged dynamical simulations that currently can't go over a certain mass scale. And so we can use that to then investigate what does the gravitational lensing profile look what does it look like for fuzzy dark matter, and are there any scales that we can pick out from actual observations of gravitational lensing that can help us differentiate between cold dark matter structure and fuzzy dark matter. And finally, the work in progress right now that should hopefully be done in a matter of a month or two is the code package that I've developed to write this paper should be publicly available for anybody to play around with very soon. This is just in last stages of making it public and perhaps publishing it on like JOS, I think the Journal of Open Source Software, for anybody to be able to use. But if you're interested, I'm happy to share kind of the beta version with anybody who wants. That's all I've got to say. I didn't mean to talk for so long. I was hoping for more time for questions, but I guess we had questions throughout. But any more questions?
You are going to look at the 2-point correlation function, things like that. So you haven't looked at this yet.
I should say that work is in progress by Sinyu, who is one of the collaborators on this.
So for instance, like the power spectrum of the fluctuations.
Is exactly what Sinyu is looking at. I mean, the key here is to pick out, in theory, and this is exactly what we're seeing, you should see some characteristic scale in the 2-point correlation function, which relates directly back to the de Broglie scale, the scale of the interference fringes. And that's exactly what we see. And the question is, can you actually, pick that out from observational data or from
some very mathematical but interesting work recently on wave turbulence. The idea that these systems are really wave turbulent systems.
Yeah, let me say a few words about this, Tomer.
And Sinyu's here.
Yeah. So
please.
For the power spectrum, what we really see is that when you subtract off this kind of the average or spherically average density profile, the fluctuation does look like something like a Gaussian distribution above the de Broglie wavelength, de Broglie scale, and then you see a sharp cutoff there.
Sinyu, I didn't even notice that you joined. Thank you for being here.
And it's more or less the same everywhere in the halo. That's what you're saying.
The de Broglie wavelength is is not exactly the same, more or less in the halo, but it's kind of roughly similar, but it's getting smaller towards the center, which also kind of contradicts with this assumption which Shive they did in deriving their core halo mass relation when they get this 1/3 scaling loss. Yeah.
So this power spectrum would not be
the spectrum shape is all the same. You have something like a Gaussian, which is flat, and then there's a sharp cutoff at the de Broglie wavelength scale.
But then this cutoff will be slightly different in the center of the halo versus the outskirts, things like that.
Yes.
And can you derive something like a Jeans equation for, to kind of include the effect of these fluctuations in some kind of, Jeans equilibrium equation, or that you get by averaging the Schrödinger equation over time, or I don't know, just guessing.
Hi, Romain. Yeah, the Jeans equation is actually already derived in the Wayne, Hu, and Bakanas and Gruzinov's this very early paper. And that's one of the very early motivation why you want to have this FDM, because you have an early cutoff in the initial transfer function and suppresses the small scale growth of the structure.
Yeah. What should I expect? If I take a star, if I had a galaxy that was just a bunch of stars, and they were not interacting, then the power spectrum would be just from pure Poisson noise, finite number of point masses. I should have something similar here. And also, if there are interactions between the fuzzy dark matter is not to lowest order, just streaming around in the mean potential of the entire system, I should get a slightly different spectrum. So is there some?
Yeah. Okay. So I mean,
you want to okay, it's all yours.
Okay, so it's mine. Okay, so actually the Gaussian spectrum is a prediction if you assume this wave is something like a random phase distribution, just something like similar to what you just said about the wave turbulence.
Yes.
So in other words, if the let's say if the amplitude follows something like a Gaussian, and they are distributed randomly in the in space, and you finally end up in the Gaussian distribution. Actually, you can go to our papers about the vortices, which is already discussed there. If you're interested, you can have a look.
Oh yes.
But so the vortices sort of scatter off each other and so on. So are these waves just moving through each other freely, or are they having some nonlinear interactions? Both
no nonlinear interaction, just free. So here, if you think of the wave function, it's just a free superposition, right?
Yeah.
Yeah.
I mean, that's an assumption, really, I suppose. You could consider some self-interactions.
Yeah, of course you can. Yeah, that's a different story.
You certainly can, but I think kind of from first principles, the typical axion-like particle, the self-interactions on the scale of 10 to the minus, for a particle of this mass scale, self-interactions are not expected to be anywhere near as important as the quantum pressure and the gravity charge. But you can, of course, treat that to get a self-interacting fuzzy dark matter particle. You just have to play with your initial scale of field differently.
Is it obvious that to this question about the Jeans equation, is it obvious that this quantum pressure that was derived for linear if I recall, wasn't this linear perturbations around the FRW in the original papers? Or is it obvious that in a halo it will be the exact the result of this averaging, or the effective fluid that you would use to describe the thing will be the same as that old Wayne Hoop and Gruzinov papers?
What the effect would be the same? Sinu actually can speak probably more directly to this, because I think look at the you know how to model this both as a fluid and as a
sure.
wave equations.
I think the answer to the Matthias question is no. And actually, we've shown in my paper in 2018, I guess, there are some examples where the quantum pressure actually be attractive rather than repulsive. So it's really a counter effect of in the Wing-Hoos paper, yeah.
Which is, I guess, a good motivation for, that's why we can't just rely on, solving these equations analytically. Why we need the full-fledged simulations and potentially something that relatively well mimics them, as opposed to being able to model this analytically.
Can I ask about this solitonic mass scaling relation? So I saw recently some papers were actually ruling out fuzzy dark matter beyond 10 to the minus 18, saying that, bulgeless galaxies cannot exist if you don't, like if you have solitons, it's in tension with these galaxies without any bulges. So can you comment on that?
I certainly have seen a few papers recently that have claimed that using these scaling relations, a Milky Way-like galaxy would have a soliton that's so big that it would be even more observable than the density cusp, for example, from just typical cold dark matter. I would caution against that because, again, these scaling relations are based on some combination of not very fully understood first principles and simulation results that are limited to a mass range that you have to extrapolate considerably to get to be able to make those kinds of claims. I think it's important to keep that in mind, and I think that's what we should be looking to solve for with this kind of work. I wouldn't say yet that is conclusive, because again, it's just taking the general form of that relation and extrapolating out to a regime where it's not in any way been tested.
And so what has been the barrier to doing simulations with a lot of variation in axion masses? Like, why haven't people already?
A major barrier for this is computational. You can't to simulate something Milky Way sized from to simulate the formation of a halo like that, and the box size that you need and the resolution you would need is not something that we currently have the computational chops to achieve. So far we've been able to, in full-fledged simulations, we've been able to simulate formation of dwarf galaxies, and all these relations come from the regime of 10 to the 8 to the 10 to the 10 solar mass halos, and then trying to extrapolate them 2 orders of magnitude higher, which is why I wouldn't necessarily say that that's the definitive last word on fuzzy dark matter.
Maybe to continue on this, naively, you would expect that if the scale that you're modeling is much larger than the Broglie wavelength, you're kind of going into some kind of classical regime, and you model the whole thing like a simple. like a classical fluid. And therefore, you might be able to have like two sets of equations that you kind of activate whether your resolution is high enough to resolve the quantum effects or not.
Good.
And
Yeah, so basically have a simulation where in the smaller box you're solving the full thing quantum mechanically, and in the larger box you're solving things with some sort of a kind of simplified fluid equation. That's a very interesting idea. I think that's something that some people are. I know it's an idea that Lam Hui pitched to me when I started working on this as a different direction we could take this. I think the challenge is, how do you deal with the boundary? How do you deal with the barrier between those two regimes? How do you deal with kind of structure that fall? You can't even think of it as a localized structure that falls into your wave part of the simulation. So I think that's definitely something that is a natural direction to take this work, or to take the broader kind of direction of the field. I don't know that there is yet a good solution to that.
Yeah, there are people in Germany like Jens Niemeyer. They are doing such zoomed-in simulations. Yeah. So what they did is mainly they evolved the n-body simulation on the large scale, and then zoom into the halo and solve for the full Schrödinger-Poisson equations. Yeah.
But I guess this that you've presented here is some way in which you're given some density profile, you find a solution that accomplishes density profile, and then you estimate by plugging in now with the phases all the fluctuations that it would produce. So I suppose if you were to consider a little piece of the halo and just say the density is this in this little piece, reproduce, just talk about that little piece, there'll be some modes, and then compute the fluctuations, will that be wrong? I mean, I'm just thinking, do you really, you see what I'm saying?
That is exactly what I would urge people to do with this. Is the question that would that be wrong? I think that's right.
Because if this is not wrong, this is some sort of path to, given some local density velocity that you are getting from the lower resolution simulation, get the effects of, get some sort of effective stress tensor and fluctuations in a little region, and then you put all the regions together or something.
Yeah, not only is that not wrong in my opinion, I think that's the main goal here is that workaround, is that shortcut to you can easily, as you said, you just basically you zoom in a certain region based on our solution, you solve for the few modes that matter there, you evolve it over time, you calculate whatever quantities you want to calculate, whether it's the acceleration field or any, basically that. And you've got what I think is a very true to the physical nature of fuzzy dark matter simulation that you did on your laptop instead of having to rely on a large kind of structure formation simulation. Of course, all the assumptions that went in are there, right? We've assumed that this density profile makes sense. We've assumed that we've got more or less a solution that correctly solves for the right distribution function. But if all those assumptions are at least close to true nature, then you should be good. That is exactly what we hope to do.
Can I add a few words? Hey, Matthias, I think this situation is kind of similar for the fuzzy dark matter as the early stage of the quantum mechanics, where people are dealing with the waves compared to the particles. Right here, so in our approach, it seems like we have to solve somehow globally to find these eigenstates and then to reconstruct these kind of fluctuations. I'm just not sure.
But why is that true, right? Is this really necessary?
I mean, because these underlying characteristics are waves. They're not just a single particle.
But which little, blob will appear or disappear in this part of the galaxy, a million, in some little time into the future, don't you think is really determined by the phase of the things in the wave function nearby now. I don't really need to know why this wave function was set out the way it was, right? Imagine that like the global thing will set up this full solution, I understand. But if I want to then look at the blobs that will appear and disappear at a given location, maybe I don't really need to know the global solution. I just need to know densities and velocities and some sort of boundary conditions in the little region that I'm interested in, or something like that.
Yeah,
because I don't think that the interference pattern here much cares about, you know, things far away, as opposed to just from the point of view that it set the whole global solution. But after that, it's probably.
Yeah, I mean, I think probably locally you can infer some information, but then you have this uncertainty principle, right? You just get, maybe you, I mean, just my personal perspective, you might get large error in the.
No, but the uncertainty principle operates over this de Broglie wavelength size or something, or what?
Yeah.
So I'm talking about a box that is bigger than the de Broglie wavelength, but still smaller than the whole region that you're interested in.
I mean, I guess you could, so let's say we wanted to zoom into, let's say, the solar neighborhood and simulate a small box in our area, right? We know the global shape of the potential, so we can put in some external potential on that box, and we can say set off some initial conditions based on, for example, you could take just one of our constructions here and populate the initial conditions, and then model kind of that in, let's say, some sort of a periodic box or something. I think that would probably not be necessarily a bad thing to do. There are, I mean, I guess I would wonder what happens. So, for example, if you were doing the full box, you would have structure from nearby influencing. And again, the waves are not localized; they are much larger. So I guess what I want to say is, so the waves that are part of that box that we've zoomed in on are just, they're fragments of the full wave. They don't.
I think Matthias is talking about a box that's maybe 10 kiloparsecs across or something. Much smaller than the overall huge halo, but big enough that you can fit in a bunch of waves. You get a 10 full wavelengths.
You get 10 full wavelengths, but I mean, but let's.
The background density is only smooth or zero.
The way, so I mean, at least kind of the solutions to the Schrödinger equation that we put out here, waves that influence the solar neighborhood are basically the size of, 16 kiloparsecs across in their diameter.
I mean, you are meaning your basis functions, psi, right? But
yes.
Isn't this like saying, oh, imagine I had done my n-body simulation in some sort of Fourier basis or something, which we usually do to compute the, forces fast. And then you are telling me, oh, but each Fourier mode is everywhere. But if we're talking about a small neighborhood and perturbations there's another way of looking at it. That's what I want.
And you don't need to think about it.
Maybe, I don't know. It's just thinking out loud. Maybe it's we're wasting people's time here too long. So.
No, I mean, I think these are exactly the questions that have pushed the research in all these directions. How do you do these things more efficiently than just taking the full box and hacking it with that very inefficient hammer?
Mm-hmm.
Because there is something like coherence in time and in space of those waves, and I guess you can try to elaborate on that, saying that very distant regions are connected through the waves, but if you randomize the information that comes from these regions somehow, it doesn't really impact the overall behavior of the zoomed region, right? Because the coherence, length scale, and time scales are finite, right?
Yeah.
Why do you say that the waves that are most impacted the solar neighborhood are 60? thought there would be some basically background and then the fluctuations of 1 kiloparsec.
This just relates to the basis, the eigenmodes that we've solved for spherically symmetrically, are all originate in the, our origin is R equals 0.
Right.
So you've got some waves that
But then
the radial waves reach all the way to the middle. The high L waves are kind of a band around a spherical shell at that.
Then I add up all the ones that are important. I draw a box around the sun, which is a few kiloparsecs or something like that. I look at the fluctuations that are left inside that box. They have a characteristic wavelength of 1 kiloparsec.
And you would need to somehow still account for the global potential that is affecting them.
Of course, yeah.
And what happens at the boundaries of your box?
Well, I know the background. I know within my box, I know what the smooth background is analytically. Let's say I fit into the NFW background state, and then I can evolve anything I want in that box on the analytical thing, plus these fluctuations on top. The fluctuations are much smaller than the box.
But are you damping the fluctuations at the edges of the box? So certainly in the middle, it would evolve for a certain amount of time reasonably, but in the dynamical time where a wave travels from one side to the other,
I guess
what
if the box
what
is
happens?
small enough, then the background is constant. I just use it as periodic.
Yes, but then sure, except that then you're assuming that a radial wave that's the radial wave exiting the top is coming in through the bottom, which is, I feel like, quite a violation of the behavior of this of an action. I mean, basically, the classical equivalent would be you've got a radial orbit and it exits at apocenter and comes out at pericenter, and that would be strange.
I mean, but we study all of these stellar dynamics in periodic homogeneous boxes. Chandrasekhar still goes on.
But we don't cut off orbits halfway through. We simulate full orbits.
We assume they get to one edge of the box and then come back the other side. Or is this not what's been done, like a shearing box simulation?
Yeah, this is
Let's go out one end, come back.
done many times. Right?
And is there a potential difference between the ends of the boxes that they're coming out in and out of? I guess I would worry about that in terms of the box edges that have a gradient of the potential in them. I don't know how. I will say, I mean, I haven't really thought carefully about this, but I suspect that those are the complications that will make it such that you're departing from the actual behavior that you'd see enough. Those would be the differences between that and just simulating the whole thing if you had the computational power to do that. I think certainly initially, when the central region, as long as it hasn't diffused outside, you'll see the right effects. But I think within a dynamical crossing time of this box, you'll start seeing departures from the global behavior that you'd expect.